Hello everyone. We have done the discussion of part 1 and 2 where we have done the discussion about the organic and inorganic questions. Now we are in the third part of the series where we'll be taking the questions of the physical chemistry of Indian Olympiad Qualifier exam in chemistry paper 1, and we have been discussing this question paper code number 31. We are talking about the objective questions. Here is the section A1 where we have got single option correct question. Going to the very first question in physical chemistry. This question was from the chemical kinetics. They tested us for all the concepts in the chapter where we were tested for which of the following options are correct. We are asked about the half-life. So we can do the discussions of all these options, which one is correct and which one is incorrect, and out of these options given, only this option number 4 is correct, rest of the options were incorrect. So how we are going ahead? We have got the reasoning. First option was half-life is 50% of the total time taken for the completion of reaction. That's not true, because half-life is when your time when A0 is becoming A0 by 2, because the time taken for the completion of the reaction is going to be nearly infinite if you have got first order reaction, because you could recall we have used to have this kind of curve for the first order reaction. So this is the time coordinate and this is the concentration coordinate. So as time tends to be infinity, then only is time going to be 0. So time taken to complete the reaction is going to be very, very long, while half-life is going to be time taken for A0 to change to its value A0 by 2. That was the case. So this first option is not correct. Second option was, second point was the collision frequency is the number of collisions per second time per unit volume is same as the rate constant of the reaction. See, the first part where they are saying the collision frequency is the number of collisions taking place per unit time per unit volume. This part is true, but this part, this is same as the rate constant. That thing is not correct, because when we are going for the, this is Z is the basically collision frequency, this one. And when we are multiplying this by something what we identify as the steric factor, because that limits number of the reactions to the number of collisions taking place, are not always translating as the number of molecules reacted. So the steric factor also must be taken into consideration. That put together, like the collision frequency multiplied by steric factor is coming as Arrhenius factor or pre-exponential factor, what we used to call. And then this A, when this is multiplied by this term exponent of minus CA by RT, that becomes the rate constant, right? So this option is again not correct. Going to the third statement, we should say, it is the change in the activation energy of a reaction at a particular temperature will result in the proportional change in the rate and rate constant. At the same temperature, that should be happening. So see, if you remember that expression, what we have just written, if we are changing the activation energy, say by X time over here, we can see the expression written just above. It tells us that by doing so, the rate constant will be changing by the value of exponent of X. So this is not changing in a proportional manner. It is change. This change is going to be exponential change, right? This is not the proportional change. This is exponential change. This is going to change in much higher way. So that's also not going to be the correct option. Moving on, we have got all the first order reactions are not unimolecular reaction. Very much true. We have seen number of reactions like all the examples of pseudo unimolecular reactions. Take the example of inversion of cane sugar. We have known the concentration depends on the rate of reaction depends on the concentration of cane sugar only. Although molecularity of this reaction is not going to be 1, the water also should be taken into consideration. And same thing happens for the acidic hydrolysis of the ester, where the concentration of the ester only is going to decide the rate of reaction, but that reaction is surely not going to be unimolecular. So if you have got the order of reaction 1, some of these reactions can be having molecularity also 1, they always should be unimolecular. That's never a bounding condition. So that is going to be the correct option. Next option was for a zero order reaction, the slope of the plot of T half versus initial concentration will be 0. For this, we actually need to go back to our zero order expression, and we used to have our relationship that for zero order reaction T half used to be equal to A naught by 2K. So if we are plotting a curve for this T half versus concentration, so if you are having this curve is plotted for T half, if we are having T half over here and versus initial concentration, that is if you are plotting for it A naught, then this is going to be having some slope which is going to be 1 divided by 2K. So whatever its slope is, that value of the slope over here, the slope is going to be 1 divided by 2K. This is not going to be 0. This is always going to be having some non-zero value. Order being 0 doesn't imply that the slope of A naught versus T half is going to be 0. So that was the question number 1. We have got only one option correct, and the first option might be sometimes confusing to some of the students. Never mind, that was an easy question if you have learned the things in the chemical kinetics. Yeah, so this is what we have seen here. The only fourth option was correct, and we have seen this solution already. So here nothing we need to write once again. We already have seen this. Moving on to the next question, that is question number 2. Here what we have, we are having the question about the kinetic theory of gases from the gaseous state. Pretty straightforward question. What we need to understand is that when we are being asked about the kinetic energy, and please note, while framing the questions, they have given us this is the total kinetic energy, this is not the average kinetic energy. And the good thing was they had given us 1 mole of neon and 1 mole of argon. Now we are asked to compare their kinetic energies and their average velocities. So we need to have the expressions for their average velocity and the kinetic energy. We have relation for the kinetic energy per mole 3 by 2 kT. With respect to that, we can calculate, because that was for 1 mole and we have been given 1 mole only, we can directly relate it, right? And second thing is the average velocity. We know that relationship 8RT by pi m, square root of that also will be giving us the so all the things are basically given. Temperature is given. For the first gas, temperature is T. For the second gas, temperature is 2D. First gas, neon, has molar mass 20 grams per mole. Second gas, argon, has molar mass 40. So temperature is given to us, molar mass is given to us. Now see how we can go ahead. The answer to this question is going to be C, that kinetic energy of the gas 1 will be twice of second, while the average velocity is going to be same for neon and argon. Let's see. The formula for kinetic energy was 3 by 2 kT. So if you are writing it for neon, maybe we can write here for the neon, and here we can write for the argon. We are writing here first thing as the kinetic energy. So how the kinetic energy is going to be? This is going to be 3 by 2 K, the Boltzmann constant, that is R by Na, that is Avogadro's constant divided by, the gas constant divided by Avogadro's number. That's going to be the same thing. Temperature over here is T, and here 3 divided by 2 K. Here temperature is 2 times T. So the ratio of the kinetic energies is going to be 1:2, because molar mass is not any deciding factor, and we can see why that molar mass is not going to decide if the average velocity is changing. When we have got lighter molecules, like in this case neon, their velocity will be relatively greater. So when we are multiplying basically m as and v square, the things like velocity being higher, molar mass being lower, both these things are being compensated, we can see from the formulae. And the situation is that kinetic energy, if you have taken the same number of mole and if the temperature was same, it would not have changed. When the temperature is being changed, when temperature is being doubled, then we are having the difference. So the idea was the molar mass over here is not the deciding factor when we are talking about the kinetic energy. The temperature is the absolute thing when we are comparing the kinetic energy. Also it comes to the number of moles, because here we have taken same number of moles. If number of moles would have been different, we would have got the different answer, right? Fine. Now going for the average velocity, we had got the formula for average velocity as square root of 8 RT by pi m. Putting that here for the neon, we are going to write, we can see here if the molar mass here is m, that is 20, then for 40 neons, the molar mass is going to be 2m. So writing over here 8 RT over here divided by pi times m, that is for neon. For argon, this is going to be square root of 8 R, that is going to be 2D divided by molar mass is going to be 2m. So 2 and 2 are cancelling out. This ratio for the average velocity is going to be 1:1. The earlier ratio was 1:2 because of difference in the temperature. This ratio is going to be 1:1 because of the difference in the temperature as well as difference in the molar mass. This would have been pi m minus t. So this is going to be the thing how we were relating the kinetic energy versus the average velocity. The confusion here could have been if you just miss this thing, that the velocity might be different but the kinetic energy would be same in spite of the fact that thing is basically that molar masses are being changed accordingly as per the ratio of the average velocity. Next question we are taking, question number 3 for the physical. This is coming from the electrochemistry, and we are asked about some reaction which is going to take place, and the Q value has been given to us. Q means that reaction quotient, what reaction is going to, whatever reaction is taking place, we are being given. So what we are saying here, the correct expression for this given thing we have to find out. So the way reaction basically has been given to us, we can see the expression what is for this basically we are talking about that Nernst equation, and in the Nernst equation we can apply it for the change where reduction can be taking place or where oxidation can be taking place. We have been given this value of the Q for oxidation converting into, for reduction, reduced form converting into oxidized form. So basically we have got some reduced form, and for any given species, and this is undergoing oxidation, something like this, and there will be some n number of electrons being lost. So that n is appearing in all our expressions. We did not bother about what was the value of n. We just need to write the values. So the answer to this question was coming as B. We are using this Nernst equation. So when we are having the value of E for this given half cell or for this given for the given species, the value we are substituting as log Q. So we can be writing here as E equals E naught minus 0.0592 divided by N. That remains the same. Now log Q. Q has been given as 10 raised to the power minus 3. So we are writing here log 10 raised to the power minus 3. Now what we all need to do is we have to just put the value of log. This whole thing basically is turning out to be minus 3. So we have just rewritten this E as E naught plus 3, like minus 3 and this minus sign and this minus 3 we have just multiplied, and here this is going to be plus 0.0592 divided by N. So now we have just rearranged E naught from the right hand side of this equation to the left hand side equation, and that is going to be the expression. This is going to be the see here there was one tricky thing they had done, that they had not told us that what this expression for the E is going to be. The confusion might have been whether this we are talking about as E naught reduction or E naught oxidation. We could have tried as per conventions, mostly things are given with respect to E naught reduction. If you do that, you won't, like if you are going ahead with this thing, there are no suitable options available, like option A, B, C, D, there are not available. So you have to think the other way around. You have to think about the oxidation reaction. Based on that, we can write the expression and we can get the desired answer. So these three questions are from section number 1. Now we are having the section number 2. Only one question was asked. This is one or more than one option correct. And this question was from thermodynamics. We are given some curve, and in this curve we have been asked going from point number 1 to point number 2, then to point number 3, and then to point number 4, coming back to point number 8. In this cyclic process, we are being asked which of the following options are correct. That is, we are being asked also what information we are given, that there is a heat exchange between the system and surroundings only in second and fourth process. Here heat exchange is going to take place, and here heat exchange is going to take place. In the process number 1 and in the process number 3, no heat exchange is being allowed. This information, if we are keeping in mind, we can read out the things, and here the option is going to be, the correct option is basically going to be this B thing only. 1 and 3 are going to be, delta S is going to be 0, and we'll see why that is happening. What we can read out from the given information, that first and third options which we are having, these cannot be the isotherms. And we understand why this cannot be isotherms, because starting from this point, this is going to be expansion, right? And because we have been given heat exchanges only for first and fourth option, that means there is no heat exchange allowed over here. If there is, in this case, there is no heat exchanged, we could have written the Q is equal to 0. So if Q is equal to 0, this is going to be, this cannot be simply the isothermal process. The reason is, if this is isothermal process, temperature is not changing, P is increasing, V is increasing. How is it possible? If it is the case of the isothermal process, then that when the gases are undergoing expansion, temperature should decrease in that process, as we have seen in usually happening in the adiabatic processes. And for temperature being decreasing, if you need to keep the temperature constant, the heat, and like this is your process, if this temperature is decreasing, then to keep the temperature constant for isothermal process, heat must be absorbed. There must be plus Q associated with this process, right? Because heat cannot be exchanged here, this cannot be isothermal process. It can possibly be adiabatic process. And now we are saying this is a reversible process. We don't have any other information. What we can read out from the given options, the pressure is being changed slowly. If pressure is, the external pressure is variable, it is continuously changing. That is how the driving force and opposing force are infinitesimally different. That qualifies this process, we can say, is going to be the process number 1 and process number 3, we can say are going to be reversible adiabatic processes. So first and third, we are saying, are going to be reversible adiabatic processes. Okay, now first, second and fourth options, the processes which are being done, we can say, because their number of moles are fixed, that we have to assume, because no information has been given when we are doing such kind of processes, we have assumed that thing in all the cases of thermodynamics as well in the gaseous state. So if we have got number of moles fixed, if it was a closed container and we have, it had to be closed, that only basically we can qualify for the condition of the heat being exchanged or heat cannot be exchanged. If number of moles are fixed, and for process number 2 and 4, pressure is also fixed, then in the process number 1, volume is increasing, temperature must increase. And when we are going for the process number 4, then temperature must decrease. That condition is qualifying as these processes can be isobaric heating as well as isobaric cooling. So now we have an idea what are the processes going on. Basis on that, we can make a decision of we can do basically the calculation of delta S, that entropy change for the first process, for the second process, third, fourth processes as well. And this we have seen, this is not going to be correct. This cannot be reversible isothermal process. It can be reversible, but this cannot be isothermal process because of that constant of the walls being or the processes being done in conditions where heat cannot be exchanged. This is we can say that the isothermal conditions are simply not possible. Now we'll be calculating delta U also on this basis of the information being given. One thing what we have not talked about earlier, this is the case of an ideal gas. And for ideal gas, the delta E is function of temperature and temperature only. Because there will be no attractive or repulsive forces present, temperature is going to give us the exact idea. E is going to be directly, delta U is going to be, or basically we should say U is going to be the function of temperature only. So that is what we are going to see this process happening once again. Process and like this pressure volume curve. The first process we have done from the point number A to point number 1 to 2. This is going to be
adiabatic
reversible compression, right? The second process was isobaric heating, because if you are increasing the volume, pressure is not changing, number of moles are not changing. How we can increase the volume? Volume can be increased just by heating. So that is going to be isobaric heating. And the next process, this one is going to be reversible adiabatic expansion. The volume is being expanded, the gas would be getting its temperature decreased. So we can also say this is going to be adiabatic cooling. And this last process, the process number 4, it was the isobaric cooling, because volume is being decreased. Volume we can only decrease when we are talking about the change in the temperature. And for these points number 1, 2, 3, 4, now we can label these processes, what these processes are going to be called as. The first process we have seen is adiabatic reversible compression, that is going to be associated with the heating effect. This one, isobaric heating. Next process, process number 3, adiabatic reversible expansion, cooling effect. And the fourth process, isobaric cooling effect, volume was decreasing, temperature is bound to decrease. Going for the calculations part, what we are writing here, the first and third process, because there are adiabatic reversible expansion, we have learned that delta S for the adiabatic processes, if you have got adiabatic reversible processes, because Q reversible divided by T used to be our delta S. So we are saying because the Q is going to be 0 for this process, the delta S is going to be 0 only. Okay, the process number 2 and 4 are isobaric heating and cooling effects. There, for such a process, we have been writing for isobaric process, we have written as the delta S is going to be NCP ln T2 by T1. So final by initial, if we are doing, this is never going to be 0, because T2 by this value of ln T2 by T1, this will be for the process number 2, this is going to be T2 by T1, this is heating, this is going to be positive. So this is going to be delta S is going to be greater than 0, and for this process this is going to be negative. Delta S is going to be less than 0. It is not going to be 0, it is going to be something different than 0. And also in the second process there is heating and cooling taking place. So because delta T is not going to be 0 for the process number 2 and 4, delta U also cannot be 0. We can say for the second process where heating is going to take place, delta U is going to be positive, and for fourth process where cooling is taking place, delta U is going to be negative. That's how only option number B was correct, where first and third process were having the delta S value exactly 0, and the all other options given were wrong. That's all in this action. Thanks for watching this video. We'll be having the last part of this discussion of this paper, that is the general chemistry, where we will be keeping the questions related with the chemical bonding, mole concept, and the the calculations which are based on atomic structures and all. That's all for now. Thank you. Bye bye. Take care.